Yeah, the same. Like when you go to some like a restaurant, like I always order like fish something like.
Well, he doesn't eat fish also.
Huh?
He doesn't eat skin.
No, he eats fish. He doesn't eat
But not the meat.
like he doesn't eat fish.
His boss name is also world boss name is same name like me. Yeah, very interesting. He's 11 years old, also Venkat. But he also has the same thing. It's interesting. You are you can understand better, right? So whenever you go to restaurants or something, you have always yeah. Yeah. It comes from, I think, neighboring state. There's one is the yeah.
Order second. Yeah, it's a good like.
Yeah, Anapur is very good actually. My Michigan State is very good. One of those good universities there. A lot of big people out there. I think that's one of the like there are something, like John
Yeah, university, but in a hospital. Hospital, university. Yeah, it's very big suburb, like about 100,000 people living in areas below.
a lot of big people out there.
Like, it's still like majority of them is students and kind of people who work.
Is it next to Wayne State medical service or
No, that's
Detroit is not a nice place to live. I know that. I think it's getting better, but
no, it's still like I have to go to Detroit because like to get my visa or passport and other things. Passport close to Detroit. 15 minute drive. It's not like pretty close. 50 minutes. Not bad. 50. 50, almost an hour. It's it's not bad.
I was told Michigan is a very safe city. I was told that my friends who lived there, they say that that's why I told he could keep the door open and sleep at night. Nobody is coming.
An hour?
Yeah, nobody is on the safe place.
Depends.
Maybe that was the case when I
Notes about robbery, about like some
Now?
show. Yeah.
did it.
You can get them robbery. Yeah. Through university, we always get all this messages, like emails about what kind of crime happening around here all the time.
Well, there was one faculty who came and joined Austin. So you must know him. His name is Vishani Kikaro. He works on melanoma.
We didn't.
He became a chair in Lake Forest now. Not a common name. All the people I know, everybody is Misha. Like,
Oh, I like to take that. What's it? Yeah,
Tasha, very everything. Dimitri is very common. Vadim. Vadim.
Vadim?
Yeah.
Yeah.
Here in Mexico. What is it called? It's not a big Maybe Jaipur.
Only goes with back on board. Board.
That's the city part. Maybe northern, maybe is it, is it northern?
A couple of people are in the issue, but like, when they get in there, people, I know the part is there.
No, it looks like.
One is there. Capital, Michigan, like, where's the capital? What you representative, like the Senate, House, everybody.
Oh, Akbar Palace, maybe the Jaipur Palace, maybe. Jaipur, the city. The palace. 50 years. 15, yeah.
Oh, so long as the longest time in my life.
Not yet.
Like, I kind of feel like it's my home country.
Oh, but it's in the United States, yeah. It's very, yeah.
I might have grown up over there.
This is, playing where you Sikh, you know, the Sikh. So there. And then, during the Sikh, it's a little bit of, combination with the Mahal. Islamic technique, so all the, that's why you see the architecture of those buildings are like a stone, like, you know, those kind of stuff. Huh? Just showing some pictures from India. You want to start here?
No,
No, it's okay.
Yeah, who's starting?
Okay. Sorry, I was a little late coming over from another meeting. So topic of presentation today is just water on Earth and how we got so much water on Earth. I always find it kind of fascinating being a scientist and working with cells to kind of take a more macroscopic look at the universe, because I think just from a day-to-day we're looking at things that are really small. So it's kind of a nice change in pace to look at something that's as massive as the expanse of the universe. So little disclaimer, I'm not an expert. I just like reading about this kind of stuff and found it incredibly fascinating. So let's dive in. So is water wet? It's a very philosophical question, but I don't think we're going to be answering that today. So as we all know, liquid water is an essential building block of life. We wouldn't be able to have a habitable planet without it. Some unique physical properties of water itself. So it's a polar molecule, basically meaning it's a non-charged molecule, but has a discrepancy of electron density. So it's a really great solvent, which means that it can transport minerals and all kinds of other great stuff from place to place in liquid form. So that gives it another life supporting property. Some strong cohesive properties. So I have this picture here of just a droplet of water coming out of a bigger body of water. So the cohesive properties create surface tension. So whenever you see water, it's always going to be, unless there's some drag or other forces acting upon it, they'll always want to form spheres, which I think is pretty cool. One other really cool thing about water is that its solid form is less dense than its liquid form. So it's one of the very few molecules that have this type of property. I think mercury is another one. But that's why your ice floats in your drinks. It ends up being less dense as a crystalline solid than the liquid form. And then also it has a really high heat capacity, which basically means that it takes a lot of energy to heat water up 1 degree. So it takes a lot to boil water, which makes it great for heat conduction. So our little special sphere, the Earth. So it's the only example that we currently know of that is an inhabited world. We could be wrong about that, but we don't yet know or have any distinctive evidence to say otherwise. For it to form, it did require a very specific sequence of planetary formation events that had to happen in a very specific sequence to actually produce the conditions that would form a habitable planet. And we really don't know at this point whether or not this sequence of events is a cosmic rarity or something that's only happened once, or if it's happening somewhere else or has happened somewhere else in the universe. The kind of infinite nature of the universe specifically probably could happen at least once in other parts of the universe. However, it might be impossible for us to observe or know that it's been happening elsewhere. So to reconcile the existence of water on our Earth requires kind of an understanding of how planets and how solar systems form, kind of from a astrological perspective. So just a little bit of a timeline sequence here. So I won't go into how stars are formed because that's a completely other talk with a lot of complexity, but essentially collapsing molecular cloud gains momentum and then kind of collapses on itself and gains angular momentum. So things are spinning really, really fast. And it's after the star forms, it's really hot. So there's a lot of chemical reactions going on to kind of basically form these pre-planetary bodies. So shortly after the star formation, I say shortly, it's kind of a few 100,000 to millions of years, we get these things called planetesimals forming. So those are basically large enough bodies of mass that are more affected by gravity than they are the hydrodynamic forces of the gases within the disk. So that's kind of one step up from the dust and gas coming together. Following planetesimal formation, we have pebble accretion, which is essentially these smaller masses of rock and ice and other kind of basic elements crashing into each other and forming larger bodies. That goes on for another few hundred million years. And then that pebble accretion is followed by gas accretion. So this is mainly what forms our larger kind of gas giant planets. I'll talk about that on a little bit more on the next slide. Following gas accretion is orbital migration. So once these bodies are large enough and massive enough, they're subject to a migration of their orbit. So their orbit changes because they're less affected by the Earth's gravity and are gaining more gravitational pull from each other, which is fantastic. Followed by that is giant impacts. So as you can imagine, after pebble accretion, there are going to be much more massive things floating around in space. So things like early planetary bodies will crash into each other, and these impacts are happening at such a force and such a speed that they end up combining and forming even larger masses. After those events happen, there's a stage called late accretion. So this is basically you have your larger bodies that are continuing to accumulate more mass at a much smaller scale than the giant impacts, but more mass gain nonetheless. And then that's followed by a final process of dynamic instability. So this is after most of the gas has dissipated from this protoplanetary disk. Then you get basically no gaseous resistance on those bodies that are inside that system. So the orbits change, and then that throws off kind of the gravitational local areas of these planets and these larger bodies. So just a little bit of a timeline here. So we start out with, I should say star, sorry, so star birth. So that's our little point over here. So once that star is born, there really aren't any large masses within that cloud, or that disk rather, because after that molecular cloud has condensed, just the speed and the angular momentum causes it to flatten out into a disk. So in that disk, there's a bunch of dust. So that's dust and kind of molecular water. And then depending on the distance from the sun at that point, or that star, you have different forms of water. So following that birth, kind of just like I was going over on the last slide, you have planetesimal creation. So like I said, those are more affected by gravity. And then we can kind of stepwise go up into how things get more massive. So after a few million years, we get pebble accretion, and then for a gas giant like Jupiter, it will start to accrete gas, and then it gets to a point where it's gotten so massive that the mass of gas actually matches the mass of the gas that's, or sorry, the mass of the gas matches the mass of the core, at which point there's a rapid acceleration of the gas accretion by that body. In contrast to a gas giant, a planet like ours, that's within the snow line. So the snow line is essentially the point in the solar system that before which all water is vapor form, because it's just too hot to have crystalline water. And then beyond that snow point or snow line, water can only exist as ice. And then as the protoplanetary disk ages and evolves, it cools because the sun gets a little bit cooler. So that snow line will migrate inwards towards the star. So we can follow this line around here. So this is obviously millions and millions of years. So the giant impacts happen around here, and then our final giant impact is actually what created our moon. So a big body ran into the Earth and basically flung off a part of mass that is now what we have as the moon in our orbit. So water chemistry in this protoplanetary disk. So there's and kind of, I guess you could call it an element called deuterium. So it's heavy hydrogen. So it's essentially a hydrogen atom with a proton. So it's H2 instead of just your kind of normal proton. So water ice that exists before the birth of the new star. So it's a very, very cold environment in that molecular cloud before there's a star. So there's some complicated chemistry that I'm not 100% certain about, but at these low temperatures, there's some ion interactions that create very high ratios of this heavy hydrogen in the water that exists at that point. So the ratio is somewhere between 10 to the negative 2. Versus the water that we have now on Earth is around 10 to the negative 5. So much, much less of that deuterium water. So after the birth of the star, it obviously gets way hot, much, much hotter because nuclear fusion is very, very warm. So this whole process creates these isotopic changes, which happen between water vapor and ionized hydrogen. So that's usually happening in kind of this white to red zone, kind of not to scale, but in that picture there. And what that does is it basically lowers the ratio of the deuterium to regular hydrogen ratio in the water in that area. So as the protoplanetary disk ages and evolves, there is equilibrium between that new kind of lighter water and the heavier water that was inherited from the pre-birth water that existed in that system. And so as this equilibrium is reached, there's a deuterium and hydrogen gradient that forms, and that ratio is very much correlated to the position of those molecules relative to the star in the system. So what that provides is when ice coalesces and kind of attaches and absorbs onto dust grains that are further away from the star, so water existing as ice, those will have distinct deuterium hydrogen ratio signatures. So depending on how far away that that water is from the star, you get a very specific relationship between deuterium and hydrogen. So now we get into the nuts and bolts of how we got water on Earth, or our Earth. We're obviously just a little bit of background. So we, in astrology or astrophysics, they kind of name one astronomical unit as the distance from a habitable Earth to the sun. So most things will be measured in that astronomical unit distance. So these first two, so there's two main models of the origins of Earth's water. So one is local accretion, and the other is delivery of water from other sources in the solar system. So local accretion was kind of a model that was proposed in a couple of different formats, but wasn't super robust, but made a lot of sense to a lot of astrophysicists. So the first thing is absorption onto grains. So basically, water vapor in kind of the inner solar system sticks to silicate grains, and then those grains are then transported through accretion to an Earth-like planet. And that potentially could account for the water budget that we currently have on Earth. But that type of paradigm would imply that the deuterium to hydrogen ratio that we should expect on Earth would be more of that is much closer to the sun. But that ends up not being the case. And it's also kind of a point against it is that water vapor kind of obviously near a star and near that heat is very short-lived. So replacing that water vapor to the point where it can actually absorb onto the grains and get accreted by the Earth is a little bit unlikely. The other possibility for local accretion of water is the oxidation of a hydrogen-rich atmosphere. So basically, this is a chemical nuclear reaction that happens in the early Earth, where at that point, the Earth is mostly just a really hot core, a hot ball of magma and liquid rock. So those high temperatures interacting with the gas that's been created by the star creates water. So that would also imply that the deuterium to hydrogen ratio should match that of the nebular gas that was around the Earth at the point that it accreted. Again, not the case. And also this had kind of been shut down by the fact that an early thick hydrogen atmosphere on Earth would most likely have just escaped into the atmosphere, which could potentially increase the deuterium to hydrogen ratio, but not to the point that we actually observe in the Earth's water today. So the other main model is water delivery, and there's several types or explanations for how that water could have been delivered to Earth. So we'll go over those one by one. So first is pebble snow. So as you might recall from the early stages of planetary formation is pebble accretion. So pebble snow is exactly as it sounds. So we have ice that cools onto grains, and then those grains interact with other grains and form pebbles. Pebbles are on the order of centimeters to meters, and then those interact with each other. So basically what we see here is 1 astronomical unit, like I explained earlier, is 1 distance from the Earth to the sun. So a habitable distance away from a star. So very early on in planetary formation, that snow line that I was speaking about earlier is well beyond that 1 astronomical unit. So ice is only forming beyond that point. So as pebble accretion happens and more ice and bigger bodies are forming, that snow line is now drifting towards the sun or towards the star as it cools. And eventually, as the solar system ages, that snow line is inside of the 1 astronomical unit, and this is not to scale, but in kind of a point where liquid water can exist. So when this all happens in this early phase of ice formation on these bodies and these planetesimals, when that ice freezes, it kind of locks in that composition of the local conditions. So that means that deuterium to hydrogen ratio is consistent, regardless, or kind of on where that ice came from, relative to its distance from the sun. The theory here with pebble snow is that once these pebbles get large enough, they are more affected by gravity and drift inwards and can then collide and interact with planetary embryos, so these kind of smaller pre-planets, and hydrate them. So this model is sufficient to kind of account for all the water that's on Earth at the moment, or that we know of. but it kind of suggests that it would have hydration from very early on ice. But what we do know is that the Earth's deuterium to hydrogen ratio of the water that's on Earth now is mainly coming from what they're calling carbonaceous chondrite meteorites. And those didn't form until much later in the kind of age of the solar system. So that's kind of been not disproven, but you know, we can't really take a great look back in time at that. So it's possible that this is an option, but this is potentially way more likely than a local accretion of water. So the next theory or model for water delivery to Earth is a terrestrial feeding zone expansion. So basically what this means is after the gas giants formed, the planetary embryos begin to grow with these other giant impacts. So bigger bodies colliding with bigger bodies. And that's usually a result of kind of the gravitational differences that are created by gas giant formation. So basically what this means is the influence of these gas giants is kind of changing the local environment of what the smaller planetary embryos are experiencing in terms of collisions, which basically shows that the Earth was experiencing a kind of a bombardment of asteroids, so very large masses colliding with the Earth to deliver its water. There's a tip in this theory or this model's cap because the isotopic fingerprint of the water that are coming from those outer asteroid belt asteroids matches the deuterium hydrogen ratio that we do observe on Earth water. However, this model doesn't account for Mars. So Mars is much smaller than the Earth. But this model would suggest that it would have a very similar bombardment and giant impact ratio. So in this model, when they do the simulations of it, Mars is between 5 to 10 times more massive than it actually is in our solar system. So there are some edits and kind of conditional requirements that can be input to that simulation that can account for Mars's current size. But it is kind of getting us towards what might have actually happened to get us our water. So the last and what ends up being the most likely scenario for water delivery to the Earth is this thing called external pollution, which is a result of giant planet migration. So essentially what happens, it was kind of similar to the last one or the last model where Jupiter forms as a gas giant first. And as that gas giant gets more and more massive, it starts to affect the local planetesimals around it. So basically what that means is this body is getting so massive that it's throwing off the gravity and the orbits of these planetesimals that are surrounding it. And as it gets larger and larger, it starts to throw those planetesimals in kind of eccentric orbits, meaning that they're not going around the sun, but rather kind of in a angular tilted fashion around the sun. So way more likely to impact other bodies in other parts of the solar system. So just to give you a little bit of context, so the colors in this figure are depicting where the planetesimals originated from. So as we progress from 5,000 years from, 5,000 years from initial planet formation, and then as we kind of go down the timeline, Jupiter's getting more massive. Saturn gets a little bit more massive, but at kind of a later time frame. But a very similar paradigm happens when Saturn gets bigger. So as we can see from the second section, is once Jupiter got big enough, it's throwing out all of these kind of initial planetesimals that were icy. into other parts of the solar system. And then again, when Saturn gets larger, it's throwing out all of these planetesimals to the other sides of the solar system. So our kind of planet is living a little bit kind of over here at that point. So within the snow line, but kind of a little bit further away from the sun at that point. But you can kind of see there's plenty of these original icy formations in and around the area that the Earth would have been. So with this, because these are kind of smaller planetesimals and they're not asteroids, they aren't contributing very much to the additional mass of the planets that they're colliding with. So essentially, instead of being an accretion, it's more of a hydration event. So that's how this model accounts for Mars's smaller size. Mars' smaller size is most likely due to just a less efficient accretion during pebble accretion in that region of Mars's orbit. A similar type of ratio between neighboring planets is seen with Neptune and Venus. I think those are the wrong planets, but two other planets in kind of the outer solar system have a similar type of mass difference that should have experienced the same accretion, but just due to the local environments that they were able to pick up mass from, there's a difference in the ratio. Similar to the previous model, the deuterium to hydrogen ratio of Earth water does match these carbonaceous chondrites, which basically is these planetesimals that are getting thrown from the outer solar system at Earth. So they match up really nicely. So this is kind of the currently most likely scenario as to how water got its Earth, or sorry, how Earth got its water. So some of you may have heard of kind of the traditional comet delivery system. So it's kind of a similar type of delivery system where we had kind of a heavy bombardment of icy like comet or icy rich comets hitting the Earth, kind of in its early life. But what that model suggests is that the comets were not contributing to the mass of the planet. So basically what this model says is that as Jupiter grew and was throwing these planetesimals towards Earth, that the water on Earth was growing as the Earth grew as well. So it's all kind of when the water we have now wasn't kind of later than its actual size. It was part of its growth. So again, a tip in the cap for this model is that it's not reliant on kind of the random collisions with comets. Obviously, back in the early formations of the solar system, those kinds of collisions were much more common than they are now, but still less so than kind of if you imagine kind of throwing a handful of rocks versus like gassing an area. There's going to be a lot more interactions between that kind of spray versus the kind of pebbles that we're throwing at each other. And then this does explain the deuterium hydrogen isotype as well as the ratio of exogenous nitrogen that we find on the planet today. So some conclusions: we do need more data. This is kind of our scientists' best guess at how this all happened, but astrophysics with new technology today are studying newly formed solar systems and kind of the exoplanets that are forming in nearby solar systems and trying to find patterns and parallels to our solar system to kind of make some conclusions on if we're correct in our modeling. But technology is getting to a point now where we can be pretty confident in our estimations and our models. And they're getting to a point where we can fit them pretty well to start them at the beginning of our solar system creation and then let them run, and they get very, very close to the situations that we actually observe now. Some new sub-millimeter telescope technologies are coming out. What I saw was in like the next 10 to 15 years, which are able to look deeper into the habitable zones of our nearby forming protoplanetary disks. These are obviously millions of years, or not millions, but several hundreds of thousands of light years away. So being able to get that technology to look at that snapshot of what's going on there should be able to illuminate some of the things that may have happened to our own solar system. That's all I got. These are my references. I highly suggest that first paper if this was interesting to you at all. It's like a 27-page paper. It's kind of a review of our thoughts on kind of how we got water on Earth. Thanks, everybody.
Great.
Question? So on Mars, there is no water in Mars history, like we
So
can.
there should have been, and there's a lot of evidence that there was a lot of water on Mars. I've read in a couple different papers that there was probably a catastrophic event that happened on Mars where a very, very large asteroid hit Mars and kind of evaporated most of the surface water and then kind of drilled down into the core of Mars enough so that any water that was in the mantle of Mars was then kind of released and degassed. So
water is essential for life. It besides that, what other planets have really like?
So no liquid water that we know of at the moment, but there's tons of ice in most or in a lot of
life species in other planets, like even as primitive as viruses.
Maybe that'd be cool. I would love to see that, but it's very unlikely that we're alone in the universe.
Yeah, I mean, some of this are very fascinating for me, but I was always curious, when from a kid, it was very good. He's always talking about astrophysics is great. But I'm very ignorant of this area. So sometimes when you are really trying to dissect more and trying to know what is there, is it more of a philosophical outlook, because for example, George was giving a talk about the Chinese, how the 5 elements came, how they have to water, and then we also did below, we like, how the 5 elements are the ones where our body is made of 5 elements. A lot of people are holistic approaches of huge are based on the systems. So I'm trying to connect this always whenever I see astrophysics, I see how is it connected philosophically tied up. And so when you are trying to do all these new telescopes and all that, what is that they are of course, from a spiritual perspective it's different. From a materialist perspective, what do they want to do? By knowing this is more for expansion of knowledge, or what type of applications for the real world these kind of studies will have?
Yeah, I mean, specifically for astrophysics, there's not a ton of real practical application for like the information that they gain. It's very much academic in kind of like being able to answer science's most kind of understood questions. And I think there's a lot of, I think most physicists are really just kind of selfish in that they want to answer the question for themselves and then contribute that to the world.
It's more like a spiritual seeker, right?
Yeah, who knows? I know a lot of people that are very fulfilled by religion, and that's how they get their fix of believing in what they believe in. But some people need answers. But who knows if the answers we're getting are actually real? But
I got from Caltech, they said, there's a 10 thing. I have 2 questions. So it's kind of interesting that the model is based on the water floating around and experimental planets in the trap in there. So that so then that's the other possibility is it's just inherent chemical reactions that you have in a habitable zone, because the model is based on the angstrom, so it's very specific sun. There are other stars that are harder or lighter, dimmer.
Yeah.
So so then if your models, the model, not your model, the model is and it's correct, and there should be other water wall very easily detected.
Yeah, absolutely.
James Webb space.
That's what they're looking for, right? So the exoplanets that they're searching for and other kind of the thing about looking into space is we're dependent on kind of the pictures we can take, and they're very much pictures of what's going on at that point in time, because we can't really take a video of what's going on millions of light years away. So we really just have to be looking at the right spot at the right time to understand, like, is that habitable zone of the planet that we're looking at, is it far enough away from the sun to be in the habitable zone, but also be at the point in its life where liquid water actually exists. So it's all very theoretical, but the fact that they can exist means that they probably should.
People detect in comment, that comment that's like water.
Crazy stuff.
What do you think would happen to the evolution of biology of like the hydrogen deuterium, heavy hydrogen ratios stayed the same? Like you said at the very beginning, like
Yeah, and a very good question. Because the carbonaceous chondrocytes that or chondrites that delivered, well, seems like delivered most of our water is probably what had most of the organic material that was the precursors to life. Or whether that came from another source later on in Earth's development is kind of a toss-up. Like you can read papers on either side of like, there's very solid arguments on both sides, but it's again just very theoretical because it happened millions of years ago. But we can kind of model it in certain ways where, like I was saying, with like planetary formation, we can do the same thing with evolution where we build out these simulations where you give it all these parameters and assumptions, start it, get it to present day and see how close we are.
But do you think something could actually like proliferate or live using these like heavy hydrogen ratios? Like I've grown bacteria in heavy hydrogen and they have a hard time.
Yeah, it's really hard to say, but like it's difficult to say whether or not the ratio that we have on Earth now is like ideal for life. Because we just really don't have any other examples of life existing anywhere else. But it very well could be. I mean, we evolved with this hydrogen or this ratio. It's very well in the realm of possibility that other life forms could prefer a different ratio of hydrogen.
Yeah, a lot of our physiology and biochemistry depends on hydrogen bonds, and deuterium will interfere with that. And also the high ratio of deuterium is just under 1%. So
Yeah,
not like everything's deuterium.
But it's only a difference in like there being a neutron there, right? But it could still hydrogen bond. I mean, that's how like heavy hydrogen gets on the backbone of a protein. There's like hydrogen hopping, or there's exchange between the heavy hydrogen and like deuterium.
Yeah, my question was how much of the Earth's mass is actually water? Because
less than 0.1%.
exactly. So I'm just trying to imagine how easy it is for a planet to lose all of its water because
Extremely easy.
yeah.
And it's like we said with the habitable zone, like the existence of liquid water is kind of a miracle. Where like liquid water itself is a very, very finite range of like, 0 to 100 C in temperature. So there's a very finite range that the planet has to be existing in a consistent orbit for liquid water to exist, because before that or any closer, it's all vapor, and any further away, it's all ice. And who knows, maybe there's life that can exist in ice, but
Yeah, but that also means that a planet doesn't require that much water to develop life.
correct.
Yeah, basically, like, if you look like on top, like area when life is here, it's basically like fill of the surface.
Yeah,
like,
the thin veneer of water
yeah,
on Earth.
It's just like,
Yeah.
even like if you go slightly above like 1 kilometer, you're already losing a lot of stuff like oxygen. Like,
Yeah.
you cannot breathe like in 5 kilometers, like that's it, it's done.
Yeah.
What about Europe? It's like a satellite for Jupiter. Like it's basically as small as it look the moon. But yeah, Europe, but like has a lot of ice. Basically, it's water. How will water appear on that?
Pretty similar types of accretion. The further out that you get inside of, I don't know the history of Europe, but from what I've read, it was most likely just that particular body was kind of an icy body that formed in kind of that early planetary formation further out, and then got trapped by Jupiter when it migrated out towards its current orbit.
It's just basically maybe like stuck each other. It's not like real like meteorite bombardier.
Yeah, and for that one, it could have been. I mean, these are very, very energetic events when these massive things hit each other. So when those things do happen, like unless that water or ice, whatever it might be, is kind of included in the minerals that are forming that body, it's likely going to evaporate and become either more ice once that cools down after the collision, or it just kind of gets lost the space.
So the Earth get its water after the moon formed? Very likely, right?
Pretty likely. Well, actually, I take that back. So in this model, this is kind of like the moon. What this is suggesting is that the water that Earth currently has is kind of inherent to after it had cooled, but was still in kind of that late accretion stage. So probably in right around like most of that water is kind of coming from Jupiter getting flung out into its regular orbit, probably around like this stage. So it could have happened kind of in the beginnings of these giant impacts, and then the moon hit, and then we probably lost a fair bit of water when the moon or when whatever hit us making the moon happen. And then yeah, the snow line kind of migrated a little bit.
There
but-
probably was water on Earth when that happened, because there is water on the moon. There is reservoirs. It's not a large amount, but there is some there.
Yeah, especially in the areas that you don't have the sun, like.
Yeah,
Yeah,
it could be
the backside.
it could be frozen water
Full.
and craters and.
Yeah.
Craters too. It's helium-3 rich because I don't think it's helium rich.
I don't have a great answer for you on that one, but coming as a kind of as our last giant impact, likely that rock or whatever the asteroid, protoplanet we'll call it, likely came from further out in the solar system. So it makes sense that it's got a little bit higher to the ratio.
So all this process happened over, several hundred years, right? So we don't have, like,
Millions of years, yeah.
nothing is going to happen that drastic during our lifetime.
Well, no.
Unfortunately, I want to build another universe.
Yeah.
Observe it. It's not
I mean,
documented,
so maybe we'll get to the point in our technology where we can build a little box and then.
Not yet, unfortunately. Sometime though.
Yeah.
Very water and moss.
Yeah, so, a lot of things, people are trying to do, when artificial, everything artificial, even cellular. And that's kind of, fictional still.
So what separates these two processes, the Quon, the gas, then?
Yeah. So it's basically just the difference between how they accreted solids. So,
Depend on their mass?
yeah, exactly. So, and it's the rate at which that mass was accumulated. So Jupiter got a ton of mass and a really quick amount of time. So once it kind of reached this point of 10 Earth masses, the gas that it then accreted matched the mass of its core, and then from there it just kind of accelerated in its size and then got way more massive. Whereas we just got hit with a bunch of hopefully smaller impacts to make us what we are. But like I said, very specific sequence of planetary formation events for Earth to be what it is. Cool, thanks guys.
Okay, all right, thank you, Trainer.
Thank you.
And whoever ordered that our lunch in our party, in the future, if you want to get together and order something, thanks to Leila for a good suggestion, and Elaine help us to purchase. Give us some idea. If you want to do it together, we can continue to do it. It will be fun. Okay. Thank you. And grab your food. Don't forget to pay, I mean, okay?
Thank you.
Yeah, thank you.
Bye.
Yeah, so very early on in kind of before the star was born, it's a very cold environment, so that type